hyperbolic sine. So let's write the hyperbolic functions. In particular, I want to talk about function that looks like hyperbolic sine of t and hyperbolic cosine of t. Okay, notice that it has the h for the hyperbolic. By definition, here's the definition for the cosine and the definition for the sine. Turn out they present some convenience in both in solving mathematical problems as well as engineering problems. This is the definition of the hyperbolic cosine, and this is the definition of the hyperbolic sine. And I urge you to read more about it. There is a whole section in the book, I think it's section 3, chapter 3, section 11. There is also hyperbolic tangent, cotangent, secant, cosecant, all the good stuff. But for the purpose of this example that I'm going to introduce, I need the sine and the cosine. An important property, similar to the Pythagorean identity in trig. You know, you have the cosine squared plus sine squared equals 1. Well, when it comes to hyperbolic, if you square and you subtract, you have 1. So instead of cosine squared, cosine hyperbolic squared minus sine hyperbolic squared equal 1. And we lose this property. Okay? So that's just one property. There are other properties. Well, let me give you two other properties. In terms of differentiation, dt of the cosine, like so, the derivative of the cosine, the hyperbolic cosine, is the hyperbolic sine, and the derivative of the hyperbolic sine is the hyperbolic cosine. So there is no negative here, like the derivative of the cosine, of course, is negative sign. Here everything is positive. Again, for more properties, go to, for more information, go to section 311. So, I'll go back to example 5 from yesterday, okay, but with an alternative solution. Yeah, this is something I normally show the honor student, and but I decided to go ahead and share it with you as well. Let's look at the notes from yesterday and see what was the problem and what was the solution yesterday. This was, if you recall, this was the last problem yesterday, example 5. Let me bring it up. The integral was dx over the square root of x squared minus a. A was positive, and because we have x squared minus a squared, one of the three standard trigonometric substitution form, this is x squared minus a squared, has the substitution a, x equal a secant theta. And we finished that and we came up with this result. Okay? What I'll show you today is the alternative solution. Again, what we're trying to do, we're trying to evaluate the integral dx over the square root of x squared minus a squared. So the solution, this time I'll use the hyperbolic function cosine hyperbolic, and I'll let x equal a times hyperbolic cosine of t, and therefore dx by the property over here will be the hyperbolic sine, will be a times the hyperbolic sine of t, and of course dt, as dx dt equals a hyperbolic sine. Okay, and now let's see what happened to the denominator once I perform this substitution. Okay, so let's look at the square root of x squared minus a squared. After substituting, you have the square root, instead of x squared, you have a squared hyperbolic cosine squared of t minus a squared. And as you factor out the a squared and you take it outside the square root, you have a times the square root of hyperbolic cosine squared minus 1. And now we are looking at this property, the property that is similar to the Pythagorean identity. And I see that if I write cosine hyperbolic squared minus 1, well, cosine hyperbolic squared minus 1 is sine hyperbolic squared. Okay, so let me write underneath in red, right there, that the radical right there is equals to the hyperbolic sine squared. Okay? And the reason being, again, if you look at this one and you solve, and then if you write cosine hyperbolic squared t minus 1 equals the sine hyperbolic squared t, like so. So I'm using this substitution here, and of course I'm taking the square root, and the denominator now will be simply a times the hyperbolic sine, like so. Okay. So this is the square root, and now go back to the integral that we started, dx over the square root of x squared minus a squared. Dx is a sine hyperbolic, dt, and the denominator is a sine hyperbolic. And this is lovely because what they end up having is the integral of dt. And of course, the integral of dt is t plus c. So the only thing that left out is to replace t. Okay, but if a is, by the substitution, is, if x is a cosine hyperbolic t, then cosine hyperbolic t is x over a, and therefore t is the inverse cosine hyperbolic of x over a. Notice that pretty much the same treatment that we would have treated trigonometric inverse function. You have trigonometric inverse function and you have hyperbolic inverse function. So the solution will be the hyperbolic inverse cosine of x over a plus a constant c. Now, if I were you, I would say, wait a second. Yesterday the solution was completely different. How can I trust this solution to be the same as yesterday? Okay. Here's yesterday's solution to the same problem. We have the natural log of the absolute value of x over a plus the square root of x squared minus a squared over a class C. Is it possible that this one that produced today is the same as this one that produced yesterday? Well, the answer is, guys, even though they don't look like the same, you can verify. There are two ways to verify. One, which is not a good way necessarily, is to take a certain value for x and a. Let's say start with x equals 1 and a equals 1 and see that you have the same result. But that will give you perhaps, you can verify that the two solutions are equal to each other for a specific value. If you want to verify it at the larger scope, is graph this one and see if the two graphs overlap. If the solutions are identical, then the two graphs will overlap. Okay? But this is definitely not trivial stuff. But notice how clean, how nice the solution is using hyperbolic function substitution. Manny, are you trying to calculate it with your calculator?